Okay, for our focus in forest ecology, most of the work that we've been doing has been leading up to this point. We're going back to looking at isoclines, and we're going to look at isoclines in the context of multiple competing species. Like I say, everything has been building up to this. There is a reason for us to look at the predator-prey population dynamics in order to understand populations of trees. But most of the time, in forestry and in forest ecosystems, we're concerned about competition. Competition for light, competition for nutrients, and competition for water among species. And now we're going to look at a framework for predicting when one species will have an advantage over the other. All right, so if you recall, we had a system of equations for competition dynamics. This is the Lotka Voltera competitive dynamics framework. Again, we got two species, species 1, species 2. They each have their own growth rates. We're going to assume that they're exponential, but they're constrained by a carrying capacity. And we've also now added in these parameters, this lambda and this delta here, which are the effect of interspecific species, interspecific species competition on the other. And if you look closely at this, it's a negative effect, and this parameter is multiplied by the population size of the other species. So this is species 2, the negative effect of species 2 on species 1, and vice versa for species 2. Now, in a biological sense, you can imagine this being competition for one of those limiting nutrients, water, light, so forth. It doesn't matter. It doesn't matter what that thing is right now. We're going to think about it in abstract terms. So what I'm going to do first here is we're going to go back to our phase space, and we're going to put species 2 on the y-axis and species 1 on the x-axis. Okay, now let's put some isoclines on here in order to understand when each species will be increasing or decreasing in its population size. Remember, the isocline is the point in this phase space where the population growth rate is 0. All right? And the way that we represent this is by first identifying the carrying capacity. And this is pretty simple to do. We simply note here on the axis for the respective species where the carrying capacity is. So we're going to have K1 right here, and then we'll choose carrying capacity for species 2. It doesn't really matter where it is. Here's K2. And then the last thing that we need to integrate here is the respective interspecific species effect. So how each species positively or negatively, it's all negative in this case, negatively affects the other. And like I said, now time to put in the interspecific species effects. And the way we're going to depict that is as a function of carrying capacity of each of these and its interspecific species effect. So first off, what we want to do is we need to identify what the effect of species 1 is on species 2. And the way we're going to do that is by having the carrying capacity of species 1 divided by the effect of the interspecific species effect of that species on it, and then we'll find another place to have the other respective interspecific species effect. So again, K2 divided by the interspecific species competitive effect. Now, by identifying these two characteristics of each species, the carrying capacity and its the influence of interspecific species composition for species 1, and then the same parameters for species 2, we can figure out where the isoclines lie. We only need 2 points to do this here. And in this case, they are a straight line connecting these 2 points. I can't really draw a straight line, but whatever. You get the idea. So these are both 0 population isoclines. Above them, population growth is negative. That means that the population size exceeds the carrying capacity. So up here, both are decreasing. Both populations are decreasing. Down here, both are below their isocyclines means that they're below their carrying capacity, and that means that both populations are increasing. Both of them are increasing. Both populations are going to increase. Now, the thing that we're really interested in is this space, where we're above the isocycline for species 2. That means that it will have negative population growth, but we're still below in positive growth space for the first species, and that means that this one will have positive growth rate. What will happen here is species 2 will have negative growth rate, and species 1 will become positive, and the whole system will grow until the way this will proceed is that species 1 will grow until it hits its isocycline, and then the whole system will travel down here to this point, K1, the carrying capacity of the first species. In this case, what ends up happening, because the effect of intraspecific species competition is lower for the first species, and its interspecific species competitive effect is pretty high, we end up having competitive exclusion. So imagine a species that is just better at certain growing conditions, grows better in a certain kind of resource environment, a particular climate, or so forth. Like hot, dry Mediterranean climate, for example, many species here would have a competitive advantage over species that are better adapted to a wetter climate or cooler climate. In that case, you would have competitive exclusion here because the population growth of the first species would continue until it reaches its isocycline, and then eventually exclude the other species and reach the carrying capacity for the first species. So competitive exclusion in a simple model, really as a function of just two types of competition, intraspecific and interspecific.